Yeah, okay.
This is just the laser.
All right. Thank you. All right. Thank you, Rob. Thank you, everyone. Thank you for the opportunity and the last 10-minute talk before the break, I think. And I wanted to update you on some progress we made on modeling on this star-planet interaction Ekaterina was speaking about, actually, and also a new observational campaign that we've conducted on HD 189733, which is one of the most iconic systems where people have looked for such kind of star-planet magnetic interactions. So now, as Ekaterina said, we've been searching for that for a long time. It's a bit elusive, but there are good reasons why we are searching for that. So if you look at the population of exoplanet, I know it's cool stars, but I wanted to show this plot here as a function of the stellar mass as a function of the stellar mass and the orbital distance in stellar radii, you have a constant orbital period along these lines. And if you try to estimate where would be a characteristic distance of the stellar wind of your star, which is the Alvent distance, so the distance at which the accelerating wind is overcoming the local Alvent speed, it would give you this red line here, which means this is, of course, an estimate, which means that all these planets in here would be orbiting within this Alvent surface and would actually be able to be in interaction with the central star. And I've taken not the most optimistic, but not the most pessimistic estimate for that. And it still gives you a number of 770 exoplanets that could be in this kind of star-planet interactions. So of course, when you know you have those numbers, you know physically this kind of interaction should occur while you want to look for them, of course. Now this is kind of my take on what's going on for that. So this is a rough idea of a rough picture of what we understand so far, how it should work. Basically, you have an orbiting planet. If you put it at rest, it sees an incoming point in flux here that is interact with the planet and maybe its magnetosphere. It has one, so it's an obstacle. And then part of the initial power or energy that is available can get transmitted towards the magnetosphere of the planet, and then you would get radio emission and some other fun stuff. But part of it can also be directed back towards the star if this planet is within the Alvent surface of the star, in the form of electromagnetic waves, mostly Alvent waves here when they are focused. And that can lead to either direct deposition of energy in the stellar atmosphere or acceleration of electrons that would then radiate either through radio emission or maybe from Bremsstrahlung when they're entering the atmosphere of the star. And I would argue that this whole thing works in the solar system, in the Jovian system. We know this is how the natural satellites of Jupiter interact with the magnetosphere of Jupiter. But we have a lot of ins and outs when you translate this system from Jupiter to a real star. And I don't have a good options today to put quantified numbers on all these hours and processes I've put here. And so when we look now at the literature, at what we detected so far, as it's been said before, it's been quite tentative. On the left, you have some tentative chromospheric emission that seem to be tied to some orbital phases of a known exoplanet. And I will come to that in a minute. And also some tentative detection in radio here from Turner in 2021. Now, what I want to convey here in this very short talk is what can we do to actually go beyond this tentative detection and try to firmly confirm it? What would be the next step to be overtaken? I want to reflect on two aspects we've been trying to push forward recently, which is first confirm the amplitude of the detected signal. So you want to assess exactly how much energy you have and how it can be actually translated in one particular observable. And also model very precisely the environment of cool stars to test the phase of the signal you actually detect. So let me go first on this one. So when we detect anything in the chromosphere, for instance, a star that could be tied to an orbital phase of the planet, can we say something about its amplitude? Well, to start to give a first answer to that, we've been using a very simple 1D model, a bit like the one that, what Takeru showed, but without non-ideal MHD effect here. And you see here on the left, you have the temperature profile as a function of distance to the photosphere and the density here. And this mainly models one flux tube that expands from the stellar photosphere. And if you plot various speeds as a function of distance here, we have the Alvent spin profile in green, in red, sorry, here. And you see that it's it varies a lot with distance. And so we have the ability to do some reflections of wave or many processes that can occur. What we do is that, in general, when you know stellar winds, you say you have some Alvent waves that are triggered by basically photospheric motion at the photosphere that will be able to ultimately accelerate or eat the environment of the star. But if you have a planet somewhere here, it can also trigger other waves that come back to the star. And how those two interact and could lead to a detectable signal is something we don't have an answer so far. If you compute what would be the typical frequency range of your Raven waves triggered by this exoplanet in orbit, you reach values between 10 to the minus 3 to 10 to the minus 1 Hertz. And so actually are comparable to the typical frequency you expect from Raven waves from the photosphere. So what we've been doing with Argo Paul, a postdoc in my group, is that we've been trying in this very simple 1D model to assess how much energy of the waves can actually go back to the chromosphere. This is a movie. You have the orbital phase. You launch some Raven waves here. This is the wave agent flex. Goes back towards the star, but hits the transition region. And most actually of the Raven waves gets reflected back towards the planet. And you have only a subpart of the wave action flux that is able to go through the transition region and gets transmitted into the chromosphere. And you see that as a function of the frequency of your wave, you have a very different result. This is a log scale in terms of how much power you can actually transmit into the chromosphere that would lead to a detectable signal in calcium-2, for instance. And so we are able to predict what would be this transmission coefficient as a function of the frequency of the wave here. And you see that it can be close to almost 1 when you are at high frequencies, but at low frequencies, you can get an efficiency factor of 0.1 or even smaller. This is very important because this frequency is tied to the size of the obstacles that drives it, okay? So it's tied to the size of the mesosphere. And the smaller the frequency, the larger the mesosphere. So here you have a trade-off. If you want to detect this kind of effect triggered from a hot Jupiter that has a very large magnetosphere, then the transmission coefficient towards the chromosphere actually drops. And so you may end up not being in a good position. On the other side, if you have a very small obstacle, then most of the energy can actually be channeled towards the chromosphere. So you certainly have a trade-off in the middle where you have still very strong star-magnetic interaction, but still are able to transmit significant energy into the chromosphere. Okay. I'm rushing because that's only 10 minutes talk, sorry. So now the second aspect I wanted to touch on here in this very short talk was to say, what can we tell about the phase of any signal that you would detect from such star-planet interactions? And so there was this paper from Coley and collaborators, actually 2 papers in 2018 and 2019, where they detected a signal for HD 189733 at one particular epoch out of 6 epoch studies. So it was really just maybe by chance they detected it. And they applied these star-planet interactions, some scaling rules using the lambda stretch and break mechanism again here, which predicts a very strong actually interaction. And they can tentatively try to estimate this value of about 80 Gauss, but again, not knowing in advance what would be this transmission factor that I was talking about before. And the question here is that can we actually confidently say this is SPI based on modeling? This is a question we would like to answer. So back in 2 years ago, we published a first paper on that, studying this same epoch that Coley and collaborators studied in August. It was observation from August 2013. And we modeled the environment of this star based on the Zeeman Doppler imaging map that was taken out at this time. And you see here that this blue bubble shows you the Raven surface of, that is predicted by the model, by this specific stellar wind model here. And the orbit of the known hot Jupiter is here in white. So you see it's mostly within the Raven surface. So that's good. And then you can follow the characteristic path of the L-size variable to see where you would be able to actually deposit it somewhere in the chromosphere of the star. You crunch the number, you put that together, and you predict what would be the power as a function of time as the planet orbits and the star rotates. And the prediction will be those orange points. And you see that the points from Coley are all over the place, but quite far from each other. And given the complexity of the eroded signal in the model, it's hard to say that if we can confidently or not attribute this signal to SPI. So what we wanted to do is that we conducted a new campaign last summer in 2023 over the month of July, combining different instruments. This is from the FIES instrument in the Nordic Optical Telescope and the Espadon at CFHT. And we took points in the calcium-2 K-band here, where we see a nice modulation of the rotation of the star. And if you take the residual of that, as was done by Coley, you get this system. And we did the same thing because thanks to Espadon data, we were able to get a ZDI map. And we did this study. And this time expanded the types of stellar wind that we consider. So for the sake of time, I won't necessarily get into all the details of the different stellar wind model. I think that's something we should actually discuss in the discussion section. What is shown that if we take the same statistical analysis tools that were carried out by Coley, we find a signal that is compatible with SPI. But if we compare the predictive signal of any of these models, so those two models, blue and red and blue and red, and try to correlate with the observed point, actually the correlation is extremely weak. So it's still, I would say that the jury is still out there. We will did an even much denser survey of the star to actually be able to confidently say this is a SPI. But this is very challenging because for a period of 2 days, you have to take multiple points a night plus have different telescopes on the ground pointing to that. But I think that as a community, if you want to really be serious about saying this is SPI or not, this is the kind of study we should put forward. And I'm out of time, I think, so I'll stop here and thank you very much.
Very nice work. I guess you don't think the conductivity of the planet to be factor.
No, that's true. So yeah, that's completely true. So for the first work, we have tried many different frequencies so that it takes and then you plug in whatever planets you consider. And also the fact is that so we did 2 experiments. One where you just do a pulse. So you as a planet just is swiping through the magnetic field of the star and then you do a pulse, that's it. Or if it's able to drag, then we constantly put in and then you have interaction from reflecting wave and wave as they're still propagating. So we do both cases and then you apply to whatever planet you like the results that we will get. Yeah. Okay.